Welcome. So I have there is a duality of giving a last talk of the day. It's a privilege and it's also a challenge. So today I will present you the Hyperion, which is our GPU accelerated quantum simulator. A few words about Qubit Pharmaceuticals. We are a drug discovery startup based in Paris with another office in Boston. We are more than 50 people by now. Started working in 2021. We have actually more than 6 drug discovery programs now. The slide is slightly outdated. And we maintain our own supercomputing cluster, which has more than 100 NVIDIA GPUs, heavily used for molecular dynamics simulations and also for quantum computing simulations. So I can actually build on the previous talks in a way. We have already seen Christian talking about doing quantum chemistry for computational chemistry. As a drug discovery company, we are also heavily interested in the insights that we can learn from quantum chemistry. We have seen that for many different systems, we can learn a lot from quantum chemistry, from the classical one done on classical computers, but also we can learn a lot from the quantum computers as well. So for those of you who don't know, quantum chemistry essentially boils down to solving the Schrödinger equation, which is this H psi equal E psi equation. So the E is the energy of the system, psi is the wave function of interest, and H is the Hamiltonian, which in our case will be molecular Hamiltonian, corresponding to a molecular system. The quantum chemistry field is a very mature field by now. It exists since for decades now. There is a number of methods available on the market. The algorithmic complexity scales from polynomial to factorial scaling for the CI methods, and the storage requirements are quite different, but they can go up to n to the fourth, where n is the number of spin orbitals, but can be lower in practice due to sparsity. However, when we move to quantum simulators, so when we try to simulate how the quantum algorithms would work, but we do it on a classical computer, we switch to the basis of qubits. So then we have to encode our problem into the power of n bits. And so as you can see, the memory complexity quickly become very challenging. So we have to store up to 2 to the power of n, 2 to the power of n elements in the Hamiltonian matrix, but actually much lower in practice. And this is what I will mention in a few slides. A few words about Hyperion. This is yet another simulator. There is a number of them already available on the market. So you might be wondering, why do we want to develop our own, and what are the things that we do differently? So first of all, we have a number of in-house algorithms. For example, the overlap adapt VQE, which has been developed by César Fenu and co-workers, which has demonstrated a very good performance for strongly correlated systems. There is an article attached to it. There is also performance concern. Hyperion provides heavily optimized sparse linear algebra routines on GPUs, and I will mention why sparsity is important later. Portability is also something we've been looking for, because we don't want to be locked to a given hardware vendor, and developing a code like this from scratch offers advantage that you can guarantee the portability from the beginning, and we actually run on both NVIDIA and AMD GPUs. And another important point is that Hyperion is interfaced with TRX-IO, which is a wave function format, open source one. And actually, via TRX-IO, Hyperion has access to many quantum chemistry codes out of the box. So it took very little development effort to have interface to many codes. So I cannot, I would just like to cite here Professor Peter Gill, who said that, do not waste time and energy treating a sparse object as if it were dense. Why is that? Quantum computing actually is essentially a very, very sparse computing problem. Here you can see example of a Hamiltonian matrix for a 14-qubit system. In dense representation, you would store 2 to the power of 14 by the 2 to the power of 14 elements, roughly 260 millions of elements. And in reality, what we get is a bit more than 36,000 elements. So only 0.01% of them are non-zeros. And so we don't want to store these zeros, because when we work in the Hilbert space, this quickly becomes very prohibitive in storage, and also in terms of computational complexity. We don't want to compute these zeros. These are actually freshly baked numbers from just produced last week, where we compared the performance of Hyperion. We did adapt VQE simulation for 500 iterations. So we are building a wave function on a quantum computer with 500 ansatz operators. And so we are running it on A100 NVIDIA GPUs versus H100 NVIDIA GPUs. H100 is the recent generation. So the timings are in minutes, and actually we see a significant gain in performance for 28 qubit, and we expect it to remain for larger systems. 28 qubits we can fit on 4 to 5 NVIDIA GPUs. A few words about interoperability. As I mentioned before, Hyperion is interfaced with TRX-IO, which itself is interfaced with all these quantum chemistry codes. And you will see in a minute why this was important for us. But basically, many quantum simulators rely on PySCF or a handful of other codes for preparing the classical Hartree-Fock or other calculation. By using TRX-IO, we are actually not blocked to a given quantum chemistry code anymore. We have access to all the codes that are presented on this slide, almost all of them. So in my title, there was a beyond minimal basis set, and so there is going to be a few slides about that. First of all, we can improve the state preparation with classical quantum chemistry. This problem has been mentioned today in several talks. Basically, we all know that Hartree-Fock is a good starting state, but it doesn't work very well for the strongly correlated systems. So we can use couple cluster simulations, but as has been mentioned before, couple cluster is a single reference method. So it also has its limitations. So we can learn from, and we can actually adopt some methods from classical quantum chemistry, such as selected CI methods. For example, there is the one I'm going to talk about is the so-called CPC method. And so if we now run overlap adapt algorithm to prepare this state, and we use the selected CI wave function as a trial wave function, which is we have a notion of fidelity, which is we measure fidelity with respect to the selected CI wave function. What has been mentioned and noticed by Cesar Finu and coworkers is that we can prepare the state which will be more accurate than Hartree-Fock, much more accurate, and the circuit required for it will be smaller. And another good thing is that we have a exact control of the fidelity. These simulations have been run with 8 NVIDIA GPUs, and so it's a simulation run with Hyperion. And as you can see on the right, already with 200 to 300 iterations, we reach a very good fidelity of our wave function on a quantum computer. And basically, there is another avenue that we can choose to go beyond the minimal basis set. One of them is to go exact, right? So we just take a bigger basis set, so we have more orbitals, more qubits, and then it boils down to doing more algebra on GPUs, well, or CPUs if you have good simulator there. On the right, you can see estimates. These are actually calculations that have been run on HPC machines. So what's the number of GPUs that we need for a certain number of qubits with Hyperion? So the 28 qubit simulation, we still fit in one node. One node usually provides 8 NVIDIA GPUs. And then for 32, sorry, this is where we start to actually spread the calculation over many nodes. So the number of GPUs is proportional to the memory requirement. It can change. It depends on the system of interest, but it can be like 7 or 8 terabytes of memory. And due to exponential scaling, you can imagine that as we go beyond that, yeah, the GPU requirements grow and grow. And for larger systems, usually you need entire HPC cluster provided to you for a couple of days, so that you can run a simulation there. But it's doable now with Hyperion. Hyperion runs with MPI, so you can spread over as many GPUs as you want. The limit is basically the HPC machine. Another way that you can try to go beyond minimal basis set is to go to use extrapolation techniques. So in this way, you use a smaller basis set to do your calculation on a quantum computer, and then you do a correction using classical quantum chemistry methodologies. There will be more about this in tomorrow's talk by our CSO, Jean-Philippe Ekmal. He's talking tomorrow morning. So if you're curious, don't miss it. And I would like to also say thanks to the amazing team of people I'm working with, especially Olivier Adjoa, who's the main HPC developer of Hyperion code from Sorbonne University, and César Finiu, who is working on all these advanced quantum algorithms for quantum computers. So, and with this, I would like to thank you for your attention.
Is there any question? So to understand what you're doing, so you're basically running a CIP-C calculation first, and then your simulator works only on that space. That's what you're doing.
So basically, yeah.
Only the selected determinants in that space.
Exactly. So we don't want to run full selected CI because this takes a lot of time on a classical computer too. So what we can do, we run selected CI up to a certain stopping criteria. So we already have a multi-reference effect because we already have determinants, like thousands of them. And then we stop when we want. And this is the trial state that we try to prepare on a quantum computer. And by changing the number of determinants, also we blend more correlation into the wave function. And this is also reflected in this state that we prepare.